Hello, welcome to this learning module. In this video, we're going to discuss the origins, the fundamentals, the background of nuclear magnetic resonance spectroscopy, NMR spectroscopy. It's our last spectroscopic tool that we're going to learn. We're going to learn two different flavors of NMR spectroscopy, both proton NMR and carbon NMR. We'll talk a lot more about that in a little bit. So let's start with reminding us what we know about spectroscopy. What we remember about spectroscopy. Spectroscopy is all about adding energy to molecules, and with NMR, the energy source that we're adding is radio waves. And that's part of the electromagnetic spectrum. It is the lowest energy part of the electromagnetic spectrum, which means it has the longest wavelength. So it is very, very low energy radio waves that we're adding to the molecule. Spectroscopy is we add energy to molecules. Molecules absorb some of that energy characteristically, and we measure that response. So with an NMR, what's happening is certain nuclei flip their spin. I'll explain what that means in a minute. And we measure which wavelengths were absorbed. And by knowing which wavelengths the molecule absorbed, that tells us something about the molecule, and we can start to determine the structure. So again, remember that each instrument asks the molecule a different question, and we can only get answers to the question that we're asking. Remember, mass spec looked at individual molecules, and we asked what was the mass of that molecule. The IR looked at individual bonds, and we asked what kind of bonds do you have, what kind of functional groups do you have. And with NMR, it's important to remember that we are looking at atoms. And we're asking what kind of atoms do you have and how are they connected? What is their connectivity? What's important to know about NMR is it's the most powerful tool that we have as chemists. It gives us information about the functional groups and their connectivity. That's something that we've never had before in any of our other spectroscopic tools. Information about the functional groups and the connectivity. Mass spec gave us a little bit of information about what kinds of functional groups a molecule might have. IR told us what kind of functional groups a molecule has, but it didn't tell us where they were in the molecule. NMR is going to help us figure out what functional groups we have and how they're connected and where they are in the molecule and what's next door. And that's really important. We've not had anything like that until now. So it is usually possible to determine the entire structure of a molecule based only on its NMR. It is almost impossible to determine the entire structure of a molecule based only on mass spec or only on IR, or even on mass spec and IR alone, because you don't know how the functional groups are connected to each other. NMR is the most important tool because we can usually determine the entire structure of a molecule based only on the NMR. All right, so how does it work? Again, I'm going to give a vague overview. There's lots of physics that goes into NMR, way more physics than I even really fully understand. So I'm not going to talk about that. I'm just going to give you a vague, broad overview. Okay, so one way to think about the nucleus of an atom. So a nucleus of an atom has the positive charged protons and the neutrally charged neutrons, and it spins on an axis. And when the nucleus spins on an axis, you can think of it like a very tiny bar magnet. And that's what this image here is showing. It's showing the nucleus of a molecule behaving as a little bar magnet with a north and a south pole. Very, very weak, very, very tiny bar magnet, but we can think of it like this. Now, this is only true, this is not true for all nuclei. It's only true if there is an odd number of protons or neutrons. They don't both have to be odd. One can be even, one can be odd, but as long as one of them is odd, then this holds that the nucleus behaves like a little bar magnet as far as NMR is concerned. So if we look at hydrogen, regular hydrogen, hydrogen 1. Hydrogen 1 has 1 proton, 0 neutrons, and 1 electron. So because 1 proton is odd, we can say that yes, proton, hydrogen is NMR active. If we look at deuterium, the isotope of hydrogen, hydrogen-2. It still has one proton, that's what it means to be a hydrogen, number of protons define an element, but it now has also one neutron, that's why it has a mass of 2. That's why it is the deuterium isotope, and it still has one electron. So both one proton and one neutron are odd, so yes, deuterium is also NMR active. If we look at, say, carbon-12, carbon-12 has 6 protons, that's what it means to be carbon, and because it has a mass of 12, that means it must have 6 neutrons, and because it has 6 protons, that means it must have 6 electrons. 6 is even, so carbon-12 is not NMR active. That's going to be really important when we talk about carbon NMR. If you remember the isotopic abundance of carbon-12, this is going to be a big problem. But if we look at carbon-13, much less abundant, it's still carbon, so it still must have 6 protons. It now has a mass of 13, so it must have 7 neutrons, and there's 6 protons, so there must be 6 electrons. Now 7 is odd, so carbon-13 is NMR active. So we'll have to talk about the implications of that when we talk about carbon NMR in a little bit. Okay, so as long as there's an odd number of protons or neutrons, then the nucleus is NMR active and it behaves like a little bar magnet. Now, if you have a sample of that molecule in a tube or a flask or a jar or something, all of those bar magnets would be randomly oriented. They would all be pointing in different directions and there wouldn't really be anything interesting or useful about it. But if you place that sample in a very, very strong magnetic field, an external magnetic field, then all of those bar magnets will snap to attention, and they'll either snap and orient themselves aligned with the external magnetic field or against the external magnetic field, and that's what this B0 term here is. B0, B sub naught, is the term for the variable for the magnetic field, the strength of the external magnetic field, and we're talking really, really strong magnetic fields here. But if you place the sample in a really, really strong external magnetic field, then all of those nuclei, those nuclear spins, align with or against the magnetic field. And you can imagine being aligned with the magnetic field is more stable, and being aligned against is less stable. You can kind of think the external magnetic field like the current of a river. If you're going with the current of the river, that's much easier. If you're trying to go against the current of the river, that's much harder. Okay, so that means that there is an energy difference then between nuclei that are oriented with their spins in line with the external magnetic field versus nuclei that are oriented with their spins against the magnetic field. And that difference in a spin state has an energy difference associated with it. And if there's an energy difference associated with it, that means that we can exploit that. That means that we can add a certain amount of energy to the molecule and cause the molecule to go from being aligned with the magnetic field to being aligned against the magnetic field. We can flip the spin of the nucleus if we apply exactly this amount of energy. And you might guess that amount of energy happens to be the amount of energy in photons in the radio wave region of the electromagnetic spectrum. So when we irradiate the molecule with radio wave energy, we can flip the nuclear spin of the molecule from being aligned with the magnetic field to being aligned against the magnetic field. And when that happens, when we do that, when we flip that spin and now it's aligned against the magnetic field, the physics term that we use for that is the nucleus is said to be in resonance. And since the nucleus is in resonance, based on the orientation of an external magnetic field, and we're looking at the nuclei of the molecule, that's where we get the term nuclear magnetic resonance. That's where we get the name from. So to recap, the molecule absorbs radio wave energy. Certain nuclei will flip their nuclear spin, and we observe which wavelengths of radio wave energy caused the nuclei to flip the spin. And we do that by looking at one nucleus at a time. We're either looking at hydrogen, or we're looking at deuterium, or we're looking at carbon-13. We don't look at, we don't usually look at more than one nucleus at the same time. Now, you might think that if we're just looking at the hydrogen, then there would only be one signal for the hydrogen because there's only one hydrogen. That's not true. When we look at an NMR looks something like this. This is a zoomed out version of an NMR, and this is a zoomed in version of that same NMR, like from about here to about here. So I'll orient us to this in a little bit. But why are there more than one signal in this NMR? if we're just looking at hydrogen. This is what we're looking at right now is a proton NMR, hydrogen NMR. And the reason is the amount of energy needed to flip the spin is a function of what we call shielding. So the amount of energy needed to flip the spin of the nucleus is a function of a term that we call shielding. And shielding is how much electron density is around the nucleus. When we have the nucleus of an atom, it's surrounded by an electron cloud, and certain parts of a molecule may have more electron density, certain parts of a molecule may have less electron density, and so there's different amounts of shielding around the nucleus. The electron cloud shields the nucleus from the big bad magnetic field, and so the amount of shielding determines how much electron density is around the nucleus, and that determines how much energy is needed to flip the spin. So different hydrogens require different amounts of energy to flip the spin based on how much electron density is around the proton. And the terms that we use, we can say more shielded. More shielded would mean more electron density around the nucleus. And less shielded would mean less electron density around the nucleus. Now, why would a molecule have less electron density around the nucleus? One obvious way that you might think about this is if there is a hydrogen attached to a chlorine or something that itself is electronegative, pulling electron density towards the chlorine. If it's pulling electron density towards the chlorine, it's pulling it away from the hydrogen, and if it's pulling it away from the hydrogen, then the hydrogen has less electron density, and therefore it is less shielded. Or similarly, if you have a hydrogen attached to a carbon that's attached to a chlorine, the chlorine is pulling electron density towards itself and away from the carbon, but it's also pulling the electron density away from the hydrogen as well. So for the same reason, this hydrogen and this carbon are both less electron density and less shielded. So we'll talk about some more of those, but that's just an example of why a certain hydrogen might be more or less shielded than another hydrogen. So that's where we get this spectrum from. In the next video, I'm going to orient you to what we're looking at in this spectrum and how we start to read an NMR and how we start to solve an NMR. But right now, that is the background, the origin of an NMR, how an NMR works. The molecule is bombarded with radio wave energy. The molecule absorbs some of that radio wave energy and flips the nuclear spin, and we measure which wavelengths are absorbed, and they produce these signals on this spectrum.